Hello, we've got some more circuit questions here. I don't think I've done these ones before, but they're all beginning to blur into one now. But I think these are new. We've got here a thermistor in a circuit in series with a 200 ohm resistor, which has got a voltmeter across it. Right, when the switch S is closed, voltmeter initially measures 8 volts. Calculate the current I in the circuit. Okay, well, the current's going to be the same all the way around, so everything's in series. Well, except the voltmeter, but there's nothing going through that really. So we can just do V equals IR for the 200 ohm resistor. So that means that our I is going to be V, which is 8 divided by 200. So 4 over 100, 0.04 amps. The potential difference VT across the thermistor. So if we got 8 across the fixed resistor, we must have 16 volts across the thermistor. Then we need the resistance of the thermistor. Well, if we've got double the voltage, we must have double the resistance compared to the fixed resistor. So that's 400 ohms. And what is the power dissipated in the thermistor? We've got V squared over R. Well, you could do I squared R. It doesn't really matter what you're going for on this. So what's that? 16 squared over 400. So that's 4 times 16 over 100, which 4 16s is 64 over 100, 0.64 watts. Right, so some quick calculations to get us started. Right, a few minutes after closing the switch S, the voltmeter reading has risen to a steady value of 12 volts. The value of the fixed resistor remains at 200 ohms. Explain why the potential difference across the fixed resistor has increased. Okay, this is one of our usual chains of reasoning that we do. So we can say as current flows through the thermistor, flows through, I'll just call it thermistor, let's just call it therm just to cut short. The temperature increases, therefore the resistance of the thermistor will decrease, therefore the potential difference across the thermistor will decrease, therefore the voltage, the PD across the fixed resistor, which is what we want across fixed resistor, will increase. So just turn those into actual sentences and then you're sorted. Excuse me. Right. The resistance of the thermistor must now be 200 ohms. So we need to say why they're the same. Well, we've got 12 volts across each. So 12 volt PD across R and T. Therefore, same resistance of 200 ohms. Right, sketch on the labelled axes of figure 3.2 over here. Possible IV characteristics. Right, for the fixed resistor, label it R, and the thermistor, label it T. Right, well, we know that it goes, well, when we've got this, steady value. Yeah, we want to go steady state. I'll come back to this in a moment. But we got 12 volts here when we've got 400 ohms in total. So when we got 400 ohms, we're going to have 0.06 amps. So we want to go through 12 0.06, and the fixed resistor is going to be straight line ohmic. So we're just drawing this straight line up through here, and that what we're labeling that R. Now thermistors, they have an upward curve when you've got I against V, because the resistance is dropping. And the resistance is 1 over the gradient in this case. So we're going to have something which is looking like this, and it's going to go through that same point. This is T, the lower curve. So we can see here that if the gradient is 1 over the resistance, as we're getting up here with a steeper gradient, we got a lower resistance, and we got a higher resistance down here. You could ask the question, well, why aren't we using these values here, where we've got 16 volts across the thermistor and 0.04 amp current? Well, it's because it's not a steady state. So you want to get a steady value here, because we've got this resistance changing around all of the time with a thermistor, or depending on what its temperature is. So you want to get it at a thermal equilibrium in order to be able to say something about the IV characteristic. When it's sitting here at 16 volts with 0.04 amps, well, that isn't representative of how it actually behaves, because these values are immediately going off and changing. So we don't want to be using these. We want to take the steady state values when it's at 12 volts with the 0.06 amps at 12 volts. So don't get caught out with those. It doesn't matter with the fixed resistor because everything's just ohmic and fine, and the resistance isn't changing around in the way that it is with the other component. Right, so that's that question. So all good. Oh, we got another thermistor here, but we've got an extra fixed resistor kicking around. EMF 16 volts, yeah, that's in the picture. Negligible internal resistance. So that's just describing everything that's in the picture, so there's nothing new in the text. Define the term electromotive force. So we can say EMF of a source is we've gone through this quite a lot, haven't we? So energy per unit charge, that's our voltage, joules per coulomb. So energy per unit charge, and then we have to say where that's going from and to. So transferred from the source to electrical energy. So that one's all fine. Not sure I can be bothered to write out the next one because it takes too much time writing all these. Explain the meaning of the term internal resistance. Right, so with internal resistance, okay, I will put it in shorthand. So internal resistance, so remember we're doing of a cell or battery, because that gives us a nice context then for what it applies to. Then we can say that it is the opposition to the flow of charge, opposition to flow of charge within that cell battery, within the cell or the battery. And this causes, so we can say which causes a voltage drop in the cell or battery, causes voltage drop in the cell or the battery, equal to the I, which we can say is the current through cell or battery, current through the cell or the battery, multiplied by little r, which is the internal resistance. Right, so yeah, two fairly long-winded definitions on those. I'm not a fan of the internal resistance one because it takes so long to write it out. The thermistor has a resistance of 360 ohms at 20 degrees C. Calculate the total resistance R of the thermistor and the 120 ohm resistor at 20 degrees C. Okay, so we've got 120 ohms and 360 ohms, right? So that's going to be 1 over 360 plus 3 over 360, 4 over 360, reciprocal 360 divided by 4, 90 ohms. So that's just doing our resistors in parallel calculation. Potential difference V across the thermistor. Well, if we've got the resistances are in the proportion of 30 to 90, so that means we can split up our EMF in the ratio 1 to 3, which means we're going to get our voltage is going to be 4 to 12. So we're going to have 12 volts across the thermistor. Then it's suggested that the thermistor in the circuit is used to monitor temperatures between 20 degrees and 200 degrees. Describe how the PD across the thermistor and the current in it will vary as the temperature increases above 20 degrees C. Right, this is pretty similar to what we had in the previous question. So we can say as the temperature goes up, we can say the resistance goes down, which means that our voltage goes down, which means also that our current will go up because the resistance has dropped. So we're just putting all of those into sentences. Battery in figure 3.1 is rechargeable. Calculate the charge stored in the battery when it is charged for 8 hours at a constant current of 1.2 amps. Right, so we're just doing a Q equals IT on this. So we're saying 1.2 multiplied by 8 hours. So 8 by 60 by 60 to get it all into seconds. So that's a 6/5 is our 1.2. So that is going to be equal to 6 cubes, multiply it by 8, divided by 5, multiplied by 100. So that is 216 multiplied by 8 multiplied by 20, which is, so what's 8 216s? That's going to be 1728. Put a 0 on and then double it. So that's 34560 coulombs. So 35000 to two significant figures. Right. After charging, the battery loses energy at a constant rate of 1.4 joules per second. EMF of the battery remains constant at 16 volts. Right, so we want to see how much energy we've got. So 16 volts, this is our 16 joules per coulomb. So if we multiply that by coulombs, we get joules. Then we need to divide by our joules per second in order to get seconds. So we want to take, we want to do 16 multiplied by this answer that we had over here, multiplied by that. So I have 34560, but I'm not actually going to use that number because I think that would be daft. Then we need to divide by the 1.4, and that's going to give us the answer in seconds. So we're going to then want to divide by 60 times 60 to give us the answer in hours, which is why I'm not going to use this 34560, because I can come back to this and the 60s will cancel. So that'd be 16 times 1.2 times 8 divided by 1.4, which is 16 by, well, we've got 6/5 divided by 7/5. So that's going to be 6 times 8 divided by 7. So we, oh, God, blimey, we've got to multiply all these things. That's 96 times 8 is 768 divided by 7. So that's 109 5/7. 109 5/7 of an hour, which is 110 hours, again, to two significant figures. Right, again, it's nice practicing a little bit of mental maths. That was a pretty straightforward question, really. There wasn't much going on in that one. What we got up next? All right, this looks like it's going to be a fairly easy start. We've got two different arrangements of resistors. For each one, we have to calculate total resistance and state something which is the same for both resistors. Right, well, this one's easy. We're just adding those together. 360 ohms, and we're going to have the same current in each one. Then on this one, then, right, so we've got, put all of these over 40 then, so we're going to have 7 over 40, so we're going to have 40 over 7 is our total resistance. 40 over 7 ohms, and then we can say they've got the same potential difference. Right, that was fine. Figure 2.2, we've got the IV characteristics. So this is what we drew out on a couple of questions ago. State Ohm's law and use the graph to explain why component R obeys Ohm's law. So for Ohm's law, we're saying that the current through a component is proportional to the PD across the component, for everything else being equal, everything else constant, e.g. temperature. So that's our Ohm's law, and then we can say why this obeys Ohm's law, because we're saying that it's the line for R is a straight line through origin, which fits with Ohm's law through origin, because that means we've just got a constant R, i.e. I proportional to V. The resistor and the thermistor can be connected to a variable voltage supply of negligible internal resistance in two ways, right? Once in series, once in parallel. Voltage of the supply is varied, so we got 0.6 amps in both, as they've marked in the diagram. Use the data from the graph to explain why the EMF E of the supply is 9 volts in this picture and then 3 volts in that picture. Right, so why would this be 9 volts? Well, we got 0.6 amps going through both of them. So at 0.6 amps, so for here at 0.6 amps, we get 4.5 volts across R and T, which equals 9 volts total, which is going to be our EMF. And then for this one, right, we've got a bit of Kirchhoff's first law going on here. We're splitting this 0.6 amps. Well, they've given us the 3 volts. What's happening here at 3 volts? Oh, we're getting 0.2 through the thermistor and 0.4 through the resistor. So at 3 volts, we get 0.4 amps in R and 0.2 amps in T, which equals 0.6 amps total. So that's fine. This is the last bit coming up here. Thermistor is now connected on its own across the terminals as the supply is set at 4.5 volts. Figure 2.4 shows the variation of current with time from the moment it's connected to the supply. Explain the shape of the graph. Right, again, it's one of these same things that we've had before. So as current flows, obviously write current rather than I, T increases, therefore R decreases, therefore I increases until T reaches, well, let's call this actually T we've got for temperature there, until thermistor reaches thermal equilibrium. So yeah, we're just putting all of that chain together again. So just write those out in short sort of bullet-like sentences. Right, yeah, they were fairly straightforward questions. I think the interesting thing is just thinking through, the IV characteristic for the thermistor when the resistance of it is changing all of the time. We can see what's going on here. As the current's flowing through, we want to get it to a steady state and then see what it's doing at that particular steady state. When things are changing all of the time, it's not exactly characteristic, is it, of the component itself? So that's something worth keeping in mind. Otherwise, these are just warm-up questions, really.